about deviations from an ideal gas law. So let's remember what an ideal gas law assumes and then talk about this concept of a deviation from or a non-ideal gas. So ideal gases assume that the particles are pretty small, that they exist at high temperatures, low pressures, and that the intermolecular forces are not significant. Remember, we said once most of these substances turn to gas, then the intermolecular forces are not present, so they can just move around wherever they want to. The non-ideal gases are going to exist at low temps. They're going to have high pressure. They're going to have significant intermolecular forces, and they're going to have a pretty big particle or molecule size. So my first year teaching AP, the way that my students remember this is they said an ideal gas is like when you go to the beach. When you go to the beach, you want to have high temperatures. You want it to be hot, but you want to have low pressure. You just want to be there chilling and enjoying the waves, enjoying the sun, and not thinking about a thing. So that's what we always remember. So an ideal gas has high temperatures, low pressure. A non-ideal gas is the opposite. It'd be like if I had to go somewhere that was cold. Let's say I had to go to Wisconsin for some sort of training in the middle of the winter, and they have feet of snow on the ground, and I'm super stressed out because I have all kinds of training. That would not be ideal. So think about the beach when you think about an ideal gas, and the opposite is going to be true. So let's do a couple questions like AP is going to ask you. So first question says, argon deviates more from ideal behavior at extremely high pressure than neon does. Which of the following is the reason for the difference? So it's saying that it's at high pressure. So already it is not ideal because we look here and not ideal is high pressure. It's already at that higher pressure. So we can't use that as an indicator. So we're going to have to look at the temperature, which it didn't tell us anything, the intermolecular forces, or the size of the particles. Well, these are noble gases, so they don't really have a lot of intermolecular forces anyways because they're not going to bond. So there's not going to be a lot of intermolecular forces. So they would be considered just to have LDFs, if anything. And so that's not going to be it. So we're going to look at the size. Argon is significantly bigger than neon. Neon is in the second period, and then argon is in the third period, so it is larger. So we would, out of these, choose A because the particle size is going to be greater. Particle volume, those energy levels are going to be bigger. Okay. Next one is an example of what a FRQ question would look like. So it gives you these two already drawn Lewis structures, and it's going to ask you some questions about it. So if I look at these, let's identify all the stuff about them first before we even start answering these questions. If they give you Lewis structures, they're going to start asking you questions about intermolecular forces and or polarity or Vesper shapes, that sort of stuff. So let's just look at these. So in this, the CH bond is considered to be a non-polar bond. This would be tetrahedral because it has 4 shared regions off of it. So if it is tetrahedral, that is considered to be a symmetrical shape. The bonds are nonpolar, so is this shape. So it ends up with nonpolar bonds and molecule. Okay, this over here is also going to be tetrahedral, which is a symmetrical shape. It has polar bonds, but since all of them are the same, it's actually a nonpolar molecule. Now let's talk about our types of intermolecular forces. So if this is nonpolar bonds, then only LDFs exist. These are polar, so we know LDF exists because everything nonpolar and polar has LDFs. But since it's a polar bond, then it's also going to have dipole-dipole. It is not going to have hydrogen bonding because there's no hydrogens in this at all. and it's not bonded to fluorine or oxygen or nitrogen. So A says, which compound has the higher boiling point? Justify your answer. The types of intermolecular forces in both substances should be included in your answer. So I would say CCl4 will have a higher boiling point because CCl4 has stronger IMFs. And if it says the types, then you need to describe them. AP will not give you points if you don't say it. So I would say LDF and dipole. And I'm running out of room. So I'm going to go over here. Has stronger IMFs than CH4, which only has LDFs. So if you have, the more intermolecular forces something has, the higher its boiling point. That's the reason water has such a high boiling point compared to a lot of substances, is because it has hydrogen bonding. It really takes a ton of energy to break that intermolecular force so that the particles go from a liquid to a gas, or even from a solid to a liquid. Okay. So then I'm going to clear this all out. So it says at 400 K, both compounds are gases. At this temperature, which compound behaves more like an ideal gas? Justify your answer, including reasoning about both molecules. So CH4 is going to be more ideal. Let's go back and look at our scenario. So ideal gases are smaller molecule particle size, high temperatures, low pressures, and the IMFs are not significant. Okay. So CH4 will behave more like an ideal gas because on the AP exam, I would probably not use shorthand anywhere. I just really do not have a lot of room to write on these screens because CH4 only has LDFs and is a smaller molecule. You can also say, instead of smaller molecule, you can say that it is less polarizable. That's another way. Remember, we talked about polarizability is the number of electrons or the number of rings. So both would be acceptable. Okay, so this would be the first part of my statement because it has only LDFs and is a smaller molecule, while CCl4 has LDF and dipole and is a larger molecule, more polarizable. Okay, and that is it. So you have to read what's given and you have to think about what's different. So in this problem, it told me that they were both at 400 Kelvin. So that's a high temperature. And so with it at the same temperature, that wasn't the factor that would play into it. I had to look at the other characteristics. So the biggest thing, and what my students in the past have done, is they just think about the big picture. Ideal gases are going to be high temperatures, low pressure. You want them to be small, and you want to have less intermolecular forces.